For all of human history, land has been the battleground of empires, the fuel for wars, and the foundation of civilizations, with even the tiniest islands being fiercely contested. But what if the next great frontier isn't on Earth, or even other planets, but in vast artificial islands we build, not on the sea, but in the heavens above? Humanity has always looked beyond the horizon, from crossing oceans to conquering the skies. Now our ambitions stretch even further, to the stars themselves, or ad astra in Latin. Space colonization is no longer just the dream of science fiction, but a growing field of serious research, investment, and debate. And in truth, it has been for over half a century, growing from the compelling vision of pioneers like Gerard K. O'Neill. In the 1970s, O'Neill proposed that space habitats might not just serve as way stations between planets, but could become the primary homes for humanity. Today, we will be looking at one of his most famous designs, Island 3, now widely known as the O'Neill Cylinder. Designed to provide a self-sustaining home for millions, the vast rotating space habitats he envisioned offer an alternative to planetary colonization, creating true islands in the sky. We've explored space habitats and megastructures extensively on this channel, from orbital stations to artificial worlds. Our megastructure compendium and space habitats episodes laid the groundwork for understanding these colossal constructions. More recently, we've examined other space habitats in detail, such as the Stanford Torus, Byrne sphere, and Hammer habitats. Today, we'll take a deep dive into the O'Neill Cylinder, exploring how it could become one of humanity's first great homes beyond Earth. I don't think I've mentioned any space habitat design more often in our discussions of the future than the O'Neill Cylinder, of which Island 3 is the best known configuration. It's probably a big reason I was offered the role of President of the National Space Society, an organization whose motto is Ad Astra, and that emerged from the L5 Society, which was dedicated to making O'Neill's vision a reality. And the development and creation of such habitats remains one of our core principles. If you're a channel regular, you probably already knew why, but if not, if you're new here, by the end of this episode, I think you'll see why. And if you are new here, I hope you take a moment to hit those like and subscribe buttons, and grab yourself a drink or a snack, as the O'Neill Cylinder is a large topic, indeed one 20 miles long and 5 wide. I'm now beginning my second term as NSS President, and I've spent much of that time collecting insight from members, many of whom have been thinking about space habitats for over 50 years. Those conversations made me want to revisit this topic because there are so many more applications and possibilities to explore, but the O'Neill Cylinder remains my favorite, and for good reason. As we'll see today, it provides the best optimization of resources to land area, the most living space for the least cost, and the most advantageous layout for human habitation. It allows for interconnected communities, forming entire orbital states. One point I want to make from the outset, one that applies to all space habitats, is how they fundamentally change civilization as we know it. Space habitats completely redefine land ownership, governance, and human expansion. Unlike artificial islands on Earth, which still require extensive real estate, space habitats take very little mass to construct relative to their size, can be designed with any day length, gravity, or climate, and exist in a place where elbow room isn't scarce, outer space. Space habitats are mobile. They are effectively spaceships, albeit not built for rapid travel, and these habitats are often factored into designs for making interstellar journeys as well. But the key difference is this: a single plant's worth of raw materials would create millions of plants' worth of habitats. One modest asteroid, rich in minerals but low on gravity, of the type we have a million of in the asteroid belt, could form its own continent worth of space habitats, whether they are built there and remain or moved to someplace someone wants them. And because they can move, they offer a revolutionary alternative to territorial disputes. If a community wants to separate, it literally can. If a region becomes overcrowded, a new habitat can be built instead of forcing expansion into neighboring lands. Separatist movements don't have to fight for autonomy, they can simply construct their own world elsewhere, or move the one they are on to a friendlier space. This is the promise space habitats offer that planets cannot. Colonizing Mars would be incredible, and with enough effort, it could even be made into a paradise world, just as Venus might one day be transformed into. But planets are few and finite. No matter how much space they offer, once they fill up, growth means conflict, whether it be diplomatic or economic conflict, all the way to outright war. Space habitats can break this cycle. So with that in mind, what exactly is an O'Neill cylinder, and how does it work? The basic function is in the name. An O'Neill cylinder is a large, rotating cylinder in space that contains a pressurized atmosphere. By spinning, it generates artificial gravity through centrifugal force. The amount of gravity depends on the cylinder's diameter and its rotation speed, so inhabitants can't have precise control over the environment inside. We've explored spin gravity in depth in previous space habitat episodes, so we won't repeat all the details here. However, this principle imposes the main structural constraint on the habitat. A cylinder can, in theory, be any length, with extreme examples like a Topopolis, a version that could stretch millions or even billions of miles. But the wider the cylinder or the stronger the gravity it generates, the greater the structural stress on its materials. This makes material strength a critical factor in determining how large and practical an O'Neill cylinder can be. All the inner surface of the cylinder's sides serve as the ground. You live inside it, with up pointing toward the central axis of rotation, and down being the interior wall of the cylinder. So in some ways it's the opposite of living on a planet where everyone lives on its surface. At either end, you have caps, which are often depicted as flat in artist renderings, but in reality they would likely be rounded or even hemispherical to better handle structural stress, even though this requires slightly more material. Unlike ring habitats, where much of the structure consists of walls or ceilings, an O'Neill cylinder is designed so that the majority of its surface area is usable land. The ceiling, in this case, isn't a true ceiling, it's simply the landscape on the opposite side of the cylinder. This design effectively makes your neighbor's backyard your sky, rather than just a piece of radiation shielding. And that radiation shielding is a key concept in space habitats, because when we crunch the numbers, we generally find that shielding requires 10 to 100 times more mass than the structure itself. Dirt and water are excellent, cost-effective shields, not just against radiation, but also for protection against micrometeor impacts. So rather than just building a barren shell, it makes sense to incorporate a landscape inside the habitat, effectively using the very ground underfoot as a protective barrier. This approach to radiation shielding is the inverse of a planet, where the sky is our thin shield from solar and cosmic radiation. In an O'Neill cylinder, the ground beneath us serves that role instead. The optimal amount of shielding is debatable, as future generations might have different tolerances. They may be far more cautious than us, or they might have advanced DNA repair and cancer treatments that make lower shielding requirements acceptable. I would guess both, that they repair radiation damage easier, but are less tolerant of having it around. You will also likely use this in tandem with magnetic deflectors and additional layers of shielding made from materials designed to handle certain types of radiation better. For any type of radiation shielding, the principle of halving thickness applies. Each additional layer of shielding has the amount of radiation that gets through. If 1 meter, or about 3 feet of soil, cuts radiation by half, then 2 meters reduces it to 1/4, 3 meters to 1/8, and so on. 5 meters, 16 feet of soil, reduces incoming radiation to a 32nd, about 3% of its original intensity, making the interior environment comparable to Earth's surface. Conveniently, 5 meters of soil also works well for creating natural landscapes inside the habitat. Most trees do not have roots that deep, and for those that do, we could reinforce the soil with strong mesh layers to provide additional anchoring. Moreover, the soil layer does not need to be uniform. Hills, valleys, and even artificial lakes can be sculpted into the terrain. We could even create elevated bubble-like platforms covered in soil for raised landscapes, or push depressions into the floor to accommodate deeper bodies of water. Building the structure out of graphene and filling spaces with aeroshells, both made from the abundant element carbon, are popular ideas, but the original version just called for plain, ordinary steel. I want to emphasize that while we will be talking a lot about the specific Island 3 design, it was intentionally designed using readily available materials and engineering from the 1970s. It was meant to demonstrate that such a habitat could have been built even at the end of the Apollo era, without relying on futuristic materials or advanced technology. Needless to say, we've made significant advancements since then. While I often discussed minor upgrades using better modern steel, aluminum, or even Kevlar, and viewed graphene habitats as a more distant possibility centuries from now, I am now much more optimistic about the near-future mass production of graphene superlaminate, GSL. Because of this, it is quite possible that we will never produce a steel or aluminum-based design at all for large-scale space habitats. A space habitat could sustain human civilization indefinitely, and may be able to maintain its structure and ecosystem entirely automatically, but if machines can do all the work, even thinking, does civilization need humans to continue? What if future space stations run forever, even after we've disappeared? That's the idea at the heart of my latest exclusive episode, Post-Consciousness Civilizations. Imagine an O'Neill cylinder, vast and thriving, except no one inside is truly aware. Could civilization become self-sustaining to the point where intelligence persists without sentience? That's out now on Nebula, the largest creator-owned streaming service, where every SFIA episode airs early and ad-free, alongside exclusive content from myself and many other fantastic creators like Real Engineering, Simon Clark, and Angela Collier. Get access to awesome Nebula originals like Tech Alters, How Circular Space Stations Conquered Sci-Fi. Sign up at go.nebula.tv/IsaacArthur to get Nebula for $36 a year. That's 40% off using my link, and explore the future of space, intelligence, and what it truly means to be alive. The reality is that an O'Neill cylinder is not going to be the first space habitat we build, especially not at Island 3 scale or larger. These habitats are designed for a future where millions of people live and work in space, and to help with overcrowding on Earth. But population growth rates have dropped since the 1960s and 70s, and so I would not expect overcrowding to be an issue on Earth this century. So we're putting people up there because there's work in space that needs doing. Even if we assume that the spacefaring population increases by a factor of 10 every generation, about 25 years, a small-scale Stanford Torus for 10,000 people would likely be built at least 50 years after a more basic von Braun wheel and at least 50 years before a full-scale O'Neill cylinder. In practice, if you had 1 million people living in space, they wouldn't all be in one O'Neill cylinder. They would be scattered across hundreds, if not thousands, of smaller facilities. Most likely, no more than 10% of the total space-based population would live in the largest single habitat, which would probably function as something like Earth's primary shipyard and spaceport, or the capital of a major nation or alliance. A true Island 3 design, capable of housing and feeding 1 million people, might not be needed until we have at least 10 million people in space, and something even larger would come much later. And this is a key point that needs to be kept in mind. O'Neill cylinders are to space development what skyscrapers are to city development, or what large suburban housing developments are to expanding towns. They are not the starting point of space colonization, but something you build once a place is already well developed. Your typical Martian or lunar dome is more like the space equivalent of a log cabin, a small, early settlement. This is also why we don't spend much time discussing the construction cost of O'Neill cylinders in today's economic terms, because we won't be building one for at least a couple of centuries unless automation advances dramatically. That said, it probably will, and if we reach the point where robots can be sent to asteroids to self-replicate and construct these habitats, then the timeline speeds up considerably. To be honest, at this point, I think if we don't have that technology inside this century, it's probably either because we got it, slipped, and got killed off by AI, or because we banned the technology, in order to prevent getting wiped out by AI, directly or existentially. In theory, we could build an O'Neill cylinder with modern manpower and technology, and space construction offers some major advantages, though it also comes with its challenges. However, actually doing so now would be so impractical that estimating modern costs is about as useful as trying to calculate the price of building a skyscraper in 1825. The basic technology for tall buildings existed back then, but skyscrapers wouldn't emerge for a few generations, when economic conditions and engineering realities had completely changed. An O'Neill cylinder masses several billion tons, so even using the most favorable modern launch costs, constructing one would cost more than the entire global economic output for several years. However, that number drops dramatically once we start sourcing raw materials from space. If a lunar base has a solar or nuclear-powered mass driver, all well within our current technological abilities, it could fling pods of regolith to a construction site for orders of magnitude less cost, where it is then processed into dirt, shielding, and structural plating. At a certain point, the cost of building an O'Neill cylinder will either become cheaper than the cost of buying an equivalent amount of land area on Earth, or simply become too small a cost to be a primary factor. Once productivity and wealth per capita reach high enough levels, a family could purchase an acre or two of land inside a new cylinder and build a home there with a reasonable mortgage. And what qualifies as reasonable to people in the late 22nd century will likely look very different from today, just as our own housing costs today are radically different from those of the past. How much land is it, incidentally? Well, as mentioned, the basic Island 3 design is 20 miles, 32 kilometers long, and 5 miles or 8 kilometers wide. We often pair it up with another too for issues having to do with rotation and wobble, but we'll get to that later. Moreover, you often see the design with large glass windows in it to let light in. Not direct sunlight, incidentally. You bounce it off mirrors that keep a steady supply of light as it turns, and which do not reflect harmful radiation, just the wavelengths you want. I do not view this as necessary. Prefer to bounce the light in through an end cap instead, onto a mirror array inside the habitat, but we do have hyper-strong transparent materials these days too. Assuming no space given over to windows or sea, you've got a usable land area inside the O'Neill cylinder that is approximately 503 square miles. That's about half the size of Rhode Island, or 2/3 the land area of my own home county of Asheville, Ohio, which is the largest in the state, and it would take just over 80 of them to match the land area of Ohio, which appropriately has just over 80 counties in total, one cylinder, 503 square miles, or 3 to 22,000 acres, or 14 billion square feet. For the other half of our audience that prefers metric, that's 1,302 square kilometers, 130,200 hectares, or 1,302,000,000 square meters, about half the size of Luxembourg. It would take approximately 100 O'Neill cylinders to match the land area of England, 275 O'Neill cylinders to match Germany, and 290 O'Neill cylinders to match Japan. Needless to say, it helps to have some water in these habitats, not just smaller lakes and rivers. But determining the ideal ratio is challenging. Earth has a roughly 3-to-1 water-to-land ratio, which is likely higher than what we want in an O'Neill cylinder. We'd also want different biomes including grasslands, large forests, mountains, tundras, and deserts, though not necessarily in the same proportions as on Earth. There's a tendency to depict these structures as mostly land, but I'd argue that coastal environments would be more desirable for residential areas. As we'll get to that in a bit, habitation cylinders are not primarily intended for large-scale food production, nor are they envisioned as isolated standalone facilities. Instead, a nation-state in space might consist of a few hundred O'Neill cylinders tethered together, alongside thousands of smaller facilities dedicated to specialized non-habitation purposes. That's far into the future, perhaps one that will never exist, since humanity may no longer need or desire terrestrial environments by then. We might all live in virtual utopias, exist as immortal cyborgs, or be nothing more than data entries in a vast computer mind that wiped us out. More likely, I suspect the future will see a diverse landscape of humans, AIs, and post-human entities, some of whom will still appreciate natural environments. And that might include the AI too. We shouldn't just assume they will all automatically like everything in steel and glass and not forest and field. Given the sheer abundance of resources in the solar system, let alone the galaxy, I don't anticipate fights to death over how a portion of these resources are used. If a faction obsessed with efficiency views space habitats as wasteful, they wouldn't have much motivation to get violent just because a quarter of the asteroid belt was allocated to building and filling such habitats. I usually estimate O'Neill cylinders as 10 tons per square meter or 1 ton per square foot, a rough approximation that could vary, particularly for dedicated agricultural habitats, which might be lighter. So too, habitats using more water surface area might mass less, as they might decide that since everyone is living on land elevated above sea level, that those spots are the only ones needing maximum radiation shielding, and the beach area would still have a lot too. Regardless, this means a default single O'Neill cylinder would have a mass of about 13 trillion kilograms, 13,000 megatons. Since the asteroid belt has only about 1/2000th of Earth's mass, you could build 250 million O'Neill cylinders just from the asteroid materials, enough to provide 10,000 times Earth's total land area. If you scrapped Earth itself for materials, you could construct enough habitats to provide a living area 4 million times Earth's total surface area, and likely several million times more than our currently usable living space. Again, there are many unanswered questions about land-to-sea ratios and how much land we need for food production, housing, and personal space. However, all the mass from the asteroid belt contains very little water. There's far more water deeper in space, where potentially millions of oceans worth of ice and volatiles exist in the Kuiper belt and Oort cloud, resources we'll need in bulk for atmospheres and biological systems, or technically Atmos cylinders. For Atmos cylinders, the weather and environmental factors would be vastly different from those on Earth. Unlike a spherical shell of air gravitationally bound to a planet where altitude causes rapid pressure changes, a large pressurized cylinder would experience much less variation in atmospheric pressure. Pressure does vary in large cylinders, but not as sharply, except in massive versions where you might have a thin outer atmosphere or Atmos cylinder. This would be the case for something like the McKendree cylinder, the larger sibling of an O'Neill cylinder. Rather than a floating island or county, a McKendree cylinder would be more like an entire continent in space. Our episode Life in an O'Neill Cylinder explores some of the environmental factors in more detail, and we've also covered processing regolith and ice into usable soil in other episodes on space farming and domes, such as the domes of Mars and gardens of the Moon. Now, a habitat this size will need to rotate about once every 2 minutes to produce Earth-like gravity, whereas a habitat with Martian-like gravity would rotate once every 3 minutes, and for lunar gravity it would be closer to 5 minutes. A habitat 4 times as wide would take twice as long to rotate. However, to have a full rotation take an entire day, you would need a structure the size of what we call a Banks orbital, a rotating habitat over 1 million miles across, which also has its own episode from last year. This means we are not trying to dump sunlight into one of these habitats through rotation alone. Instead, we could spin it on a different axis once per day to allow sunlight in, but a more practical approach would be to simply leave a window in an end cap and direct light through it using mirrors, adjusting intensity and spectrum as needed. When constructing several hundred square miles of landscape, adding a similarly sized area of tinfoil-thin mirrors is not a significant challenge. Some proposals suggest placing 2 habitats next to each other and using an array of mirrors to alternately illuminate one and then the other, effectively creating alternating day and night cycles. However, I doubt it would be practical to have different time zones in adjoining habitats. Instead, those mirrors would likely be redirected toward other energy-intensive systems. The emphasis here is on having many movable mirrors, not just a few giant ones. But you might decide it's best to have a community running 24/7 and then alternating day and night might be nice, and then your 12-hour AM/PM setup might be easier than our current time zones. You always know that if it's 2 PM your time, then anyone in the other cylinder is at 2 AM, essentially a mirror habitat to your own. If you only want one time zone for your habitat, then one use for these mirrors could be agricultural cylinders, where lighting and climate could be optimized for specific crops, allowing for productivity far beyond that of modern farms or even greenhouses. As a rough estimate, an O'Neill cylinder habitat dedicated entirely to agriculture could feed a few million people. However, such structures would likely be built using only a fraction, perhaps as little as a tenth, of the mass of a typical habitat, since they wouldn't require as much shielding. Even if livestock were included, additional shielding could be selectively applied to barns. Cancer is not contagious, so while increased mutation rates could be a concern due to radiation exposure, this would be a long-term issue, one that could be mitigated by periodically introducing fresh stocks from locations with better shielding and environmental controls. Additionally, agricultural structures wouldn't require as much infrastructure. Gravity could likely be kept lower, as some evidence suggests this may aid plant growth while having no impact on microorganisms. They may also benefit from having longer daylight periods. These facilities also wouldn't need the same level of expensive shielding and hyper-redundancy as a more complex, inhabited habitat. If people were living there, their personal homesteads could have increased gravity and additional shielding in the walls and floors, with protective gear available for work in the open farm areas. More likely, however, these facilities will be dedicated to crops that require minimal crews, while more personnel-intensive agricultural operations would be housed within standard habitat cylinders. You only come to these when it's harvest time in your tractor with extra radiation shielding and an airtight cab. You can also keep crops staggered so you are always harvesting one or another. You might wonder why hydroponics isn't the primary choice, as it's often discussed for space use. The simple reality is that while hydroponics makes sense on spaceships, where mass constraints are critical, space habitats require shielding anyway, so using soil is just as practical. For more on this topic, check out our episodes on space farming and agricultural and farming planets. If we do assume we can use something like graphene superlaminate, GSL, for a habitat, and assuming the same redundancy and safety margin used for Island 3, except for the increased tensile strength, which is almost 200 times stronger, this allows us to contemplate a habitat over 1,800 miles or nearly 3,000 kilometers wide. Again, that is the McKendree cylinder, first discussed in the 1990s, and would have around 40,000 times the living areas as an identically proportioned Island 3, hence why we call them continent-class habitats, which also covers the Bishop Ring. See that episode for details, though it might be time to give each of those their own look too. There's certainly enough material to discuss. We don't necessarily need two stations together for counter-rotation, though spinning cylinders do present gyroscopic issues. The same effect can be achieved by having a second, slightly wider and more massive cylinder nest inside the first, counter-rotating, potentially at a slower rate. This inner layer could serve as an agricultural zone and a storage area for excess water and materials, providing additional shielding. You could nest multiple habitat layers or even the primary habitat as the outermost one. There is always the question of how to handle the fact that your sky is essentially your neighbor's backyard. One solution could be a nested cylinder, essentially a thin, lightweight inner shell painted blue, or even a massive TV screen displaying a daytime or nighttime sky. In reality, I don't think this would bother people much. The central axis would contain mirrors for natural lighting, as well as microgravity facilities, and you'd still have clouds. Between incorporating hills, valleys, and overhead structures to break up the view, potentially even using permanent aerogel cloud banks with their own low-gravity ecologies, I think most people would find this an acceptable trade-off, especially compared to planetary alternatives. An O'Neill cylinder presents the challenge of creating an artificial sky, but offers complete control over weather, temperature, climate, day length, and gravity, something Mars or Venus cannot provide. There's also no natural view of space from inside, but simple airlocks could allow houses to have an underside chamber with a small pressurized dome for stargazing. However, since the habitat rotates every few minutes, the view wouldn't be like our night sky. Instead, would likely function more like a window with a blast shutter, located in the equivalent of a garage for a personal spacecraft. Such spacecraft would be much easier and cheaper to build for interhabitat travel, as they wouldn't require atmospheric re-entry tolerances or high delta-V capabilities. If we assume this station is in Earth orbit or at a Lagrange point, and part of a network of similar habitats, the average person could own a personal ship, allowing them to travel freely within cislunar space. You have obvious radiation issues if you hang out in your garage or hangar for the view, but honestly I suspect by the 22nd century, even that radiation in low and regular doses won't be a serious health concern anymore. I think you would have transparency on at least one of the cylinder caps, but I expect you would roll blast shutters over them at night. As mentioned, I don't think transparent sections would be any larger than necessary, nor would there be mirrors bouncing light between habitats. However, if a second agricultural layer existed within the slower rotating superstructure, that might be an exception. Instead, I believe any excess light during the station's nighttime would be redirected toward energy-intensive applications, such as refining metal, producing fuel, or general manufacturing. And as mentioned, I never assume one of these stations is hanging out by itself in the void, but rather nest inside some large superstructure where many other facilities are at, all sharing some basic shielding, magnetic deflection, and point defense systems. All those huge, thin, cheap solar collectors and mirrors and radiators also act as free shielding against debris and micrometeors too. The general assumption is these habitats are built to accommodate a growing population. However, many believe humanity has already reached its peak population and may need to focus more on maintaining numbers rather than expanding living space. I disagree with that perspective and am skeptical of the entire narrative, but that's beside the point. The future will have different factors influencing population growth, likely including vastly extended lifespans, enhanced birth control technology, and improved fertility methods and windows. As a result, our current population trends are about as relevant to the long-term future as those of the 20th century, the 12th, or even the 2nd century. But even if we don't need the population space, what else would we use one for? One consideration is ecosystems. While most would function just fine within the baseline Island 3 size, we can certainly build larger habitats. However, I suspect most cylinder habitats will be as small as circumstances permit, since larger structures require stronger materials and come at a higher cost per unit of living space. Smaller cylinders also allow for more specialization, tailoring each to specific needs or preferences rather than relying on a single massive habitat. Your local capital might actually be in the smallest habitat in a conglomeration too, as it might be the original habitat the others were built as growing room for in later times. That said, larger habitats will inevitably be built where necessary, such as for preserving large ecosystems. For instance, if you want to create an elephant preserve, you might need tens of thousands of square miles to properly sustain it. There are tricks for linking multiple habitats together in a way that allows birds to travel between them, or even fish and land animals if needed. Nothing prevents you from arranging long cylinders along the edge of large 3D shapes, such as an icosahedron, then wrapping the entire structure in a massive sphere of solar collectors. This setup would create a protected, low debris and low radiation interior space that could house additional facilities. Another approach is to create vast chicken wire-like meshes of habitats. Perhaps we need an episode on those, but for now, we'll simply note that arbitrarily large networks of space habitats can be arranged in a way that permits regular animal life to move between them. You can also connect O'Neill cylinders end-to-end like sausage links, or extend them into arbitrarily long structures, such as the Topopolis. For more on that, see our episode Topopolis the Eternal River. Or a rung ward setup, rung not ring, where many O'Neill cylinders are placed in parallel like the rungs of a ladder, connected at both end caps to a larger, thinner cylindrical habitat, such as a Topopolis. These structures can be insanely huge without requiring exotic materials, creating a single, interconnected habitat system millions of times more spacious than Earth. This is another episode I probably ought to do, especially now that modern modeling and graphics allow us to better visualize some of these structures. I remember how difficult it was to find good graphics a decade ago, and how time-consuming it was to make them myself. As I like to say, the cool thing about the future is that there's always more of it. This is technically episode 496, one of the last before we switch numbering systems. Depending on how we count, it's actually either episode 721 or episode 661. I figured we keep the current system through episode 500, and I'm still nowhere close to running out of topics. We could talk about O'Neill cylinders for hours, and some of the episodes I've mentioned explore fascinating details on their environments and construction, but I want to close with two final topics: asteroid mining settlements and interstellar arcs. First, I believe many asteroid mines will require human presence and will be gold mines not just for raw materials, but for economic growth. These will start as small outposts but will naturally expand as their mining production funds further development. I also think many O'Neill cylinders will be built on and inside asteroids, as we discussed in asteroid settlements. These locations will likely evolve into interdependent communities since they'll be far enough from Earth or other planets to require self-sufficiency. As we've noted before, a successful space colony cannot function with just a few hundred people. Once a settlement reaches a certain size, it needs multiple layers of governance, from lawyers and judges to specialists and doctors, roles that AI can assist with, but not fully replace. At least not without AI sophisticated enough to replace humans entirely, or simply count as people and thus citizens needing their own services too. The last role is in regard to interstellar arc ships. Interstellar travel presents one of the greatest engineering and societal challenges humanity could ever undertake. Amongst the most commonly proposed solutions are arc ships and generation ships, vast self-sustaining spacecraft designed to carry entire populations on journeys lasting centuries or even millennia. while many designs focus on fusion-powered craft, light sails, or even black hole drives to get the ship there as fast as you can, one of the most practical approaches may be adapting O'Neill cylinders for the task. These massive rotating habitats could serve as interstellar arcs, providing stable, Earth-like environments for long-duration missions, both for the colonists and for the huge amounts of flora and fauna they will need for terraforming. Unlike smaller, more constrained spacecraft, an O'Neill cylinder-based arc could house entire ecosystems, allowing for large-scale agriculture, advanced manufacturing, and diverse social structures to persist across generations. It can also serve as their home when they arrive, as they are not likely to find much beyond barren and dead worlds when they get there, and so they may live there for more generations and use it as a hub to expand on as they grow in space and down on some new world. The main advantage of using an O'Neill cylinder for an interstellar journey is that it wouldn't feel like a ship at all, it would feel like home. Traditional generation ships run the risk of cultural and psychological stagnation, with future generations potentially forgetting or rejecting their ancestors' mission, but a well-designed O'Neill cylinder could provide a self-sufficient, expanding civilization, allowing for a population that grows and evolves naturally over time, rather than one confined to a strictly managed, ship-bound existence. Multiple O'Neill cylinders can even be linked together, forming a rungboard-style structure, ensuring redundancy and adaptability. Some might even argue that a civilization living in such an environment could travel indefinitely, colonizing new systems along the way rather than simply seeking one final destination, and we call these gardener ships, as they simply grow in number during journeys, stop in a system to resupply and let some colonists depart, and move on to the next strange new world. These sorts of habitats may be what they colonize a new system with too, as many systems may not have planets worth terraforming, but will almost certainly have plenty of smaller rocks to work with. In that sense, these interstellar megastructures wouldn't just be transported to another world, they'd be the foundations for humanity's permanent expansion into the cosmos. Fundamentally, as we move into the next frontier, the high frontier, or even the final frontier, O'Neill cylinders offer a way to transplant not just human communities, but entire civilizations and ecosystems. They provide a scalable method for expansion, allowing us to replicate thriving societies by the trillions, ensuring that every culture on Earth can have its own space to flourish while still leaving room for countless more to come. These habitats may be islands in space, but they can form vast archipelagos, interconnected yet diverse, each a unique world unto itself. They represent a future where humanity is not confined to one fragile planet, but instead spread across the stars with a trillion new places to call home.